Hello everyone, Mr. Boltri here bringing you video 1.6 of AP Physics C, in which we're going to be introducing the calculus concept of integrals, integration, and antiderivatives. So in order to do that, we are going to revisit the power of VT graphs, talk about what is an integral and how does it tie to physics, and then give you the power rule for integrals just like we did for derivatives. So first, let's just go back and look at VT graphs to see how useful they can be. And first, by just answering a little warm-up question of looking at this VT graph between 0 seconds and 10 seconds, just after 10 seconds, what is the position of the object? And hopefully you didn't fall for my trap and rejected the question, because we cannot determine the final position of the object using this velocity versus time graph. The reason that is because this velocity versus time graph has no information about initial position. So we could find the displacement of the object between 0 seconds and 10 seconds, but because we don't know where the object started, we can't say where the object ended. But if we were to find the displacement of the object between 0 seconds and 10 seconds, what would we do? And hopefully we remember that the area between the function and the horizontal axis of a VT graph gives us the displacement, because that's just basically knowing how fast the object was going for how long. And then when we find the area, which is going to be a velocities or some velocities times the times, that's going to give us the displacement. And then if we have some really powerful tools, we could figure out what the position versus time graph looks like. And you'll notice that I have several position versus time graphs here, because it could be any one of these, or hundreds and thousands and millions more, because it could be at any different starting position. But you'll notice that in every situation, the path looks pretty much the same, just with a vertical shift, because we don't know the starting position. But we do know all the different velocities at all the different times. So in every situation, the curvature looks the same. And also, you'll notice that in every situation, the displacement looks like it's 300 meters. So it doesn't matter where we start, we're always going to end with a displacement of 300 meters ahead of where we started. So now that we have that unlocked, what if the VT graph looks something more like this? Could we then find the displacement of this using our triangle method? No, because this does not fit in a triangle. It's a curve. So we're going to need a more powerful tool to figure out what is this area in order to answer this question. And even a step beyond that, what if we wanted to know, well, what is the actual function of the position versus time, given this velocity versus time? We here have a quadratic velocity versus time. What does the position versus time look like? What is the actual function? So it looks like this, and you'll notice again we have the vertical shift. But can we write the function for the position versus time graph? That would, if we could find the area of this curvy VT graph, and or write the function for this extra curvy position versus time graph, that would be really cool, right? Hope you agree that integrals are really cool. So what is an integral? Well, an integral or an antiderivative, and I'm going to use those pretty much interchangeably. There is a small mathematical difference, but it's so small that it doesn't really matter that much for this course. It basically is the opposite function of taking a derivative. So what I mean by that is if I take the antiderivative of some function f prime of x, it's going to give me f of x, which is the function that if I then take the derivative of f of x, it gets me back to f prime of x. So you can sort of move up and down like that. So let's do a specific example of how do integrals tie in with physics. And let's say we have a velocity versus time function of 7. Well, what does that mean for our position versus time graph? Well, hopefully you recognize that that means that the position versus time graph has a slope of 7. And we don't know the initial position, so it could be a whole bunch of initial positions, but it has a slope of 7. So it's going to be 7t plus some sort of initial position that we don't really know right now. So because it could be any one of these, it could be 100, it could be 60, it could be 0, it could be negative 23.5. We're just going to say, well, we don't know the initial position, so all we know is 7t plus c is some initial position that we don't know and we can't know just by looking at the velocity versus time graph. So that's where that plus c comes from. So if we start with the velocity versus time graph, and we take the derivative of the velocity versus time graph, we end up at the acceleration versus time graph. So then what happens if we take the antiderivative of the velocity versus time graph? Well, hopefully you'll recognize that gets us back at the position versus time graph. And what if we take the antiderivative of the acceleration versus time graph? Well, since it's the opposite function of the derivative, it gets us back to the velocity versus time function. Again, with still the plus c, because we don't know the starting position in the first case or the starting velocity in the second case, just how much the position changed, how much the velocity changed. Let me do just a little bit of integral notation just so you're always getting it right. So there's two flavors of integrals. There's the indefinite integral, which gives you the function. So if I did the indefinite integral of the velocity versus time function, it would give me the position versus time function. So there are some names for some things that you might want to know, but you don't need to memorize these. It just allows us to talk a little bit more technically. So here you have the integral sign, and the thing that you are integrating is called your integrand. And always remember your variable of integration, which is something that even sometimes I forget, but it's so important because it tells you with respect to what variable are we taking the integrating this integrand. And then what this gives you is the antiderivative, which is the function that then if I took the derivative of this function, we would end up back at the integrand. And then always you need to make sure that if you're doing the indefinite integral, you add your constant of integration. And that just says, well, we don't know where vertically the function is, but it could have any sort of vertical shift. And you'll notice that on the left, this is kind of what you're going to be seeing more in math class. And on the right is going to be what you're seeing more in physics class, because we're dealing with time instead of x's and velocity and position more in physics class than just random functions, which you're doing in math class. So then not the opposite, but the other flavor of integrals is not the indefinite integral, but it's the definite integral. And the definite integral gives you a value. So for example, if I do the definite integral of the area of the acceleration function between 0 seconds and 10 seconds, we know that the area of the acceleration versus time graph gives us the change in velocity. So that would give me how much the velocity changed, the number for how much the velocity changed between 0 seconds and 10 seconds. Or if you just integrated the function f of x between the random points a and b, it would just give you the area bounded between the function and the horizontal axis between points a and b. So there's definite integrals and indefinite integrals, and we're going to see just in a second how both of them can be useful in different circumstances. So I've been talking about, well, you just do the antiderivative, find the antiderivative, just integrate it. But we haven't talked about how you integrate something yet. So in order to figure that out, let me just reiterate to you that the antiderivative is the opposite mathematical function of taking the derivative. So in order to do the opposite mathematical function, you just need to do the opposite thing in the opposite order. So let's look at the power rule for derivatives and think about what we're doing in what order. So first, we take the power and multiply it by the front. And then we reduce the power by 1. So what would you say is doing the opposite things in the opposite order? Well, first, if we start with some function and we want to take the antiderivative, we have to do the opposite thing, which is increase the power by 1. That was the last thing we did when we were taking the derivative, the first thing we're doing when we're taking the antiderivative. And then, instead of multiplying that power by the front, we are going to divide the front by that power. And then we end up with the function that we started with, though we should probably include a plus c here, just because we don't know what the initial position is given this velocity versus time function down here. But that is how you take the antiderivative. That's the power rule for antiderivatives. So now let me show you an example. By going back to the question that I asked at the beginning of this video, given this velocity versus time function, what is the area between 0 seconds and 5 seconds? Which we know if we find the area of a velocity versus time graph, that still tells us the displacement between 0 seconds and 5 seconds. So we're given the function here of the velocity versus time graph, which is going to be probably the most common thing you're going to be given in an AP question. They love to start with the velocity versus time graph because then you can take the antiderivative to get up to the position versus time function, or you could take the derivative to get down to the acceleration versus time function. So they love to start with the velocity versus time graph, which is why we're doing it here. So given this velocity versus time graph, if we wanted to find the area, well, that's just the displacement. So if we were able to make the position versus time graph that corresponds to this velocity versus time graph, we could just choose any one of these and we could find the display. We could do final position minus initial position, and that would give us the displacement. So first, we're going to use the indefinite integral, because you'll notice that I don't have an a or a b here. We're going to use the indefinite integral of the velocity versus time function to tell us the position versus time function. So here I need to, I kind of spoiled it because I wanted you to practice the power rule, but we end up with this as the position versus time function, 4t cubed plus some c, which these functions all follow 4t cubed, and they're all at different initial positions, different plus c's. So now that I have this as the general equation for the position versus time function, I can actually do a final position minus initial position using that 4t cubed plus c. And you'll see this sort of bar notation. This just means, so this is our position versus time function, and we want to do final position minus initial position. The final position at 5 seconds minus the initial position at 0 seconds. Since this is our position versus time function. So you'll notice, well, shoot, I don't have a plus c. Should I choose 0? Should I choose 100? Should I choose 66.2? And I'm going to show you that it actually doesn't matter what you choose, so probably choose something really easy like 0. But I'm just going to leave it as plus c, and we'll see that final minus initial, the plus c is basically going to disappear. So you don't even, past this example, have to include it. But if we evaluate this at t equals 5 seconds, we get this. And then doing final minus initial, if we evaluate it at 0 seconds, we get this. You'll see that c, whatever we choose, minus c, is going to cancel out. So that's the reason why most of the time when you're doing a definite integral like this, you just ignore the plus c. So we get 4 times 5 cubed minus 0. We get the displacement of this object between 0 seconds and 5 seconds is 500 meters. And so that is the power of integrals. Don't worry if that was a lot. It was a lot. Don't worry if it was a little overwhelming. We are going to be practicing that again all year. Make sure you let me know if you have any questions that I can address in our next class. This is Mr. Boltri wrapping up our Calculus Introduction to Integrals, video 1.6, and go Bears.